In another talk, I might motivate computer formalization, but for this audience, I know I don't have to do that. What I thought I would do, though, is briefly give an overview by reviewing the abstract. So I'm going to talk about my particular subject area, which is something called infinity category theory. And I'm not going to assume you have any sense of that, but one thing that is distinctive about the literature in infinity category theory is that authors often try to avoid using a precise definition of an infinity category theory. And you can imagine that creates some sort of an impediment to formalization. So what I'm going to talk about in this talk are sort of three broad strategies that would kind of get around that impediment, which I'll refer to as analytic, axiomatic, and synthetic, and I'll explain what I mean by each of these. And then I'm going to talk about parallel ongoing collaboration efforts to formalize infinity category theory in two different proof assistants following the latter two of the strategies. Now, first one, these are sort of ongoing collaborative projects. It would be great to have more contributors. So if this inspires you to join the effort, that would be awesome. And I think these comparative formalization projects are kind of interesting because they allow us to sort of see some advantages and disadvantages of each approach. And so I'm going to try and highlight that as much as possible. Okay, so first, so that'll be sort of the plan. So first I want to explain a little bit what I mean by, the literature tries to develop the theory of infinity categories without using a definition of infinity category. So here's a famous example of this. This is a paper that Jacob Lurie wrote during his PhD, a preprint really on infinity topoi that was later greatly expanded and became the book Higher Topos Theory. And this is one of many, many, many examples that avoids using precise definition of infinity categories. He says, we'll begin with an informal review of this theory. There are many approaches to the foundations of this subject. What you can read about approaches to the foundation, meaning like in particular, a definition of infinity category that Bourbaki would recognize. So that is, fully precise in the standard foundations of mathematics. Rather than single out any one of those foundations here, we shall attempt to explain the ideas involved and how to work with them. The hope is that this will render this paper readable to a wider audience, while experts will be able to fill in the details missing from our exposition and whatever framework they happen to prefer. So the idea was to give sort of higher level arguments. Sometimes these are called sort of model independent arguments, and then sort of leave the details of compiling it down to the foundations, to the reader. So you can imagine this is sort of a pleasant reading experience, but in terms of formalization, it's quite challenging. What is an infinity category, sort of very, very roughly? I will expand on this later. It's a category, so it has objects and morphisms, but then it's an infinite dimensional category. So it has two-dimensional morphisms and three-dimensional morphisms and four-dimensional morphisms, countably infinitely many dimensions. And then also all the category axioms are weak. And that's sort of why this is a complicated notion. If we did the strict analog of this, it would not be nearly as complicated as the weak axiom. So associativity is to some higher morphism that's invertible in some sense, and then you have to ask about coherence of associativity and higher associativity and all of that. And that's the thing that is painful to make precise in the language of set theory. This is not so we refer to sort of selecting a set theoretic definition as choosing a model. This is not a model in the sense that a model theorist would recognize. So it's not sort of a precise theory that has many models. It just means a precise set theoretic definition, but that's the way in the field folks refer to this. Okay, so let me say a little bit more about the idea. So, firstly, what's an ordinary one category? So here's the definition that appears in the Lean proof assistant. So there's an underlying type, which are the type of objects. That's the capital V here. Then there's a dependent type of arrows. So given two objects, so two terms of type V, there's an arrows from X to Y. It's denoted HOM XY. Lean actually uses two different notations for the HOM type, which are available on this slide and always annoys me. I guess in VS Code, I can't point and click, but this long arrow that appears in the definition of composition, for instance, is the other notation in Lean for HOM types. So then there's some structure. There's a specified identity arrow from X to X for any X. There's a composition function, and then there's some axioms about that. That's the ordinary definition of a one category. So a more precise idea of what an infinity category is, and this distinguishes infinity categories, which are sometimes called infinity one categories, from other weak infinite dimensional category, is that we're going to replace all of these types by something called an infinity groupoid. It's also known as a homotopy type. It's also known as an anima. And what that refers to is it's sort of the information of a topological space encoded by all of its homotopy groups. So for example, like the disks in any dimension, all of those have trivial homotopy groups. And so even though, you might think of a point in a solid ball as being, or an infinite plane as being very different topological spaces, they all represent the terminal infinity groupoid. So they're the same as infinity groupoid. And then as we suitably weaken all these structures and axioms. So composition in particular is not, it's best not to think of it as sort of a well-defined function, but maybe a function that's defined uniquely up to a contractible space of choices. But then if you're forced to make a choice, then you have to worry about coherence issues and so on. So it's all a little bit complicated. Okay, so what I want to transition into now is the first of three strategies to make this theory formalizable. And the first one I'm going to call is analytic. And what that means essentially is that you can't formalize anything with this vague definition of an infinity category that I gave you on the previous slide. To be able to formalize, I need to actually pick a definition. So the most popular one is now known as quasi-category, following Andre Riehl. It was originally introduced by Michael Boardman and Rainer Vogt under the name weak Kahn complex. And this is in MathLib, by the way. And what is the definition? So I'm not going to explain this because if you've seen this for the first time, it's sort of pretty unclear, but it's a concrete thing. It involves this S, which is some sort of functor that satisfies some condition. And infinity groupoids, those are the sort of homotopy types or anima, can also, in sort of the same model, be described as functors with the same shape, satisfying a slightly different condition. But the point that I want to make is that relatively few results have actually been formalized with these technical definitions. So they've been in MathLib for about a year. They're very, very well known in the field. If you ask somebody to give a model of an infinity category, there's lots of folks out there who know this definition. It's not an unfamiliar thing. And actually kind of a funny story, until last week, or I guess 2 weeks ago now, the definition of Kahn complex was wrong. There was there's something in here that parameterizes over all natural numbers, and essentially we needed to move the n to the n plus 1. And this mistake was such that had anybody been using this definition for anything, it would have been caught, because the definition sort of was so that there are basically no examples of Kahn complexes, but MathLib hadn't formalized any examples of Kahn complexes. So, nobody noticed that the definition was totally wrong. So, why are these definitions, it's a concrete thing. If this were the focus of this talk, I could totally explain all of this, but why is this so hard to work with? Why have so few things been formalized with them? So, I mean, firstly, I guess maybe the complexity is connecting that definition that I just showed you back to the idea of an infinity category is really a bit complicated. So the idea, again, is we take this definition of an ordinary category, and then we replace all these types, which in Lean should be thought of as sets, by infinity groupoids. There's also the axioms, which I left out to give a little more space on the slide. So in particular, if we are thinking of infinity category as a quasi-category, we would have to do various constructions. So there's something called the maximal subcomplex in a quasi-category that gives this infinity groupoid of objects. So that's this thing that's replacing this type capital V. You can do, the category of simplicial sets is Cartesian closed. And so you can form this exponential, mapping from delta 1 to S, and then pull back along a certain thing. And that defines an infinity groupoid of arrows between these two things. Proving that is a Kahn complex is a bit delicate. That's the sort of thing that requires an argument. And then you can show that this n-area composition, again, it's not really well defined as a function, but it's well defined up to a contractible infinity groupoid of choices. And the point is none of this has been formalized in MathLib just because it's all a bit of a pain. And also, it's also not that useful. I mean, these are conceptually important facts in connecting this specific analytic definition of infinity category back to the idea of an infinity category, but they somehow don't come up as often in proofs. So it's not clear that this would be the first thing you would try to formalize. So now I'm going to introduce the three sort of strategies for formalizing the theory of infinity categories. The first is to, give precise analytic definitions of an infinity category in some model. So in particular, using the formal definition of quasi-category that was given already, and then just sort of bite the bullet and prove theorems about infinity categories using that model. In the literature, we refer to this as something that involves a lot of combinatorics. I mean, it's not combinatorics in the sense a combinatorialist would think of combinatorics, but there are a lot of sort of iterative inductive arguments involving gluing together a whole bunch of simplices that one has to do. So that's one strategy. And there are people who are working on that strategy. So there are various, there's essentially nothing in MathLib currently that reflects that strategy, but there's a lot of kind of forks of MathLib and branches of MathLib where there's significant work in progress along the analytic approach. So strategies 2 and 3 are quite different. And essentially, it's like what you might try to do if you don't want to do this analytic approach. And one of them is what I'm going to refer to as the axiomatic strategy. The idea is that I'm going to axiomatize the category of infinity categories. There's a particular axiomatization, which is called an infinity cosmos, which I'll say something about a bit later. And then state and proof theorems about infinity categories in this sort of axiomatic language. And then, ideally, you want to show that this is non-vacuous. So you need to prove that some model satisfies the axioms, and that's kind of where the hard work will go. So this is kind of, formalizing something that's more abstract because the specific example that you care about is too hard. And then strategy 3 is somehow even more radical. So we're going to avoid the technicalities of set-based models by developing the theory of infinity categories synthetically. So not in traditional foundations of mathematics, but in some domain-specific type theory. So the idea here is essentially change the background foundation so that an infinity groupoid is a much easier thing to access. An infinity category doesn't naturally involve a whole lot of sets, but it does involve a bunch of infinity groupoids. And so if you could just sort of directly access these infinity groupoids, then you could give a definition of infinity category that's a lot more similar to the intuitive idea, which is like it's basically just an ordinary one category, but you replace all the types by infinity groupoids. A challenge there for formalization is we're formalizing in a sort of bespoke axiom system, a bespoke formal system. And so you need a special proof assistant that's designed to understand the rules of that. But such a thing exists. It's called RZK or Rusk, after Charles Rusk. And that's what I'll tell you about in the second project. So if it's okay with the seminar organizers, I feel like this is a good place to stop and see if there are any questions. And then what I'll do for the rest of the talk is say more about the ongoing project, which implements strategy 2, and then the ongoing project, which implements strategy 3.
Sure. It doesn't look like there are any questions in the chat. I'll just double check again. I think.
I don't think. Yeah. Okay.
And I'll check with the audience over here. There is one question.
It looks like
Great.
Your definition earlier of a quasi-category, you have the or infinity group as a Weber-Seidel and Prop didn't make. How come Weber-Seidel and Prop that previously you've needed these higher types, if I was correct?
I didn't hear all that. Could you repeat one more time?
Yeah, so
Would you like to come closer?
Okay, yeah, so quasi-category here resides in Prop, while previously Quiver have had to reside in a higher universe. How come you're able to compress all of the higher universes into just Prop in this case?
Got it. So a quasi-category, so simplicial set, which is the definition I haven't expanded here, that's the capital S set. I can't highlight, so but right before prop, that is not a prop, that's data. So a quasi-category is the data of a particular functor. It's a functor from some certain category valued in types. And so that's where the data is contained. And then to make such a functor into a model of an infinity category, you add a condition, and the condition is just the proposition.
Okay, so
yeah, so this looks like it's in prop because all you're seeing here is the axioms. So the axiom is analogous to saying there exists composition. Composition is associative. composition is unital or something like that. But the data of the sort of the objects of the morphisms, the two morphisms, the three morphisms is in this simplicial set, which is not a proposition, that's data. So,
Nice, thank you.
sure. Other questions?
Are there any other questions? There's one question at the back. Would you like to come over? Yeah.
Is it possible to use directed type theory to formalize infinity categories? I know that Page North had some work on this, but I'm not sure if it ever went anywhere.
Yeah, that's right. So the domain-specific type theory that I'm going to talk about in the Strategy 3 project is a form of directed type theory. It's a form of directed type theory that's sort of optimized for infinite dimensional categories. But yeah, it's similar to things that Page North has done, though not that type theory specifically.
Thanks. There don't seem to be any other questions in the room, and I'll just have another look at the chat. Yeah, it seems to be empty.
Okay, well, press on. So great, thanks for that. So, all right, so I'm going to tell you now, so there are other folks who are working on this first strategy, the analytic definition of infinity category using quasi-categories in Lean, at least, perhaps another proof assistance. I'm not involved in that, so I won't say anything more, but I'll tell you about some projects that implement Strategy 2 and Strategy 3. And what's more complicated here is explaining like what it even is we're trying to achieve. So sort of setting up the hope is that ultimately the formalization will be easier, but sort of the conception of the formalization is certainly more complicated and also more challenging to explain, but I will do my best. So this is this approach that we called axiomatic. How you would find about it on the web is under the name Infinity Cosmos Project. Infinity Cosmos is a particular axiomatization of kind of a theory of infinity categories. This is due to myself and Dominic Verity. The project has had early essential contribution from Mario Carneiro. And we're taking advantage of sort of the standard Lean workflow. So there's a website that contains a blueprint and which is a LaTeX file, which is kind of cross-linked with the Lean repository. So points directly to definitions in MathLib when they exist. There's a dependency graph that's generated by such a thing that can help folks keep track of like which lemmas are formalizable and which things require more prerequisites before it's time to attack them. Pietro Montecone helped me set all this up. This is built on infrastructure of Patrick Massot, and we're using Zulip very heavily to discuss like what it is we're trying to do. So new contributors should look for us there. Okay, but let me try and explain a little bit of the idea of what it is we're trying to achieve. So the aim is to average existing, so, you know, Lean's mathematics library has a lot of stuff in already. And in particular, it has pretty extensive theory of one categories, also two-dimensional categories, either two categories or bi-categories, really both of them. And then also enriched category theory. So this is a sort of category that has objects, but then the HOMs are objects of some other category as opposed to just types. And we're going to use those notions to formalize basic infinity category theory. How does this work? So the idea is we're developing the theory of infinity categories more abstractly using this axiomatic notion called an infinity cosmos. And what it is it's one of these enriched categories whose objects are infinity categories. And in particular from an infinity cosmos, so this is some huge category whose objects are infinity categories, I can, you know, quotient it really and extract a two category. So two categories, a two-dimensional category is objects are infinity categories, morphisms are the functors between infinity categories, and two cells are the natural transformations between infinity categories. And then there's this thing called formal category theory, which means that you can derive definitions of things like adjunctions and colimits and con extensions. You can develop some of the theory of infinity categories just working with this two category. And in fact, some of that is MathLib already. So in particular, like a correct definition of adjunction between infinity categories is an adjunction inside this particular two category that we construct from an infinity cosmos. And then there's a whole bunch of theorems about adjunctions that you can prove at that level of generality. And in fact, some of this has been proven in MathLib already. So facts that you might know, that if you have, two left adjoints to the same functor, they're isomorphic. In other words, there's a infinity natural transformation that's invertible connecting them. Those sorts of results, are true at this more general level, and the proofs at this more general level are just much easier than compiling all this down to some statement about quasi-categories. So that's the idea of this project. And there's one thing that will be hard. So, really what we're developing in the Infinity Cosmos project right now is kind of this abstract theory. So from this axiomatic notion of an infinity cosmos, all of these theorems follow, or all these theorems hold about the objects in an infinity cosmos, in other words, about infinity categories. What'll be difficult is proving that this is non-empty. So showing that quasi-categories defined in infinity cosmos will be hard. And this is something where we're really going to rely on the folks who are developing the analytic theory of quasi-categories in Lean. But the hope is that this will increase the payoff for doing so. So my impression is that proving anything about in the analytic theory of quasi-categories is quite painful and quite difficult. And rather than have that pain sort of come back at every new lemma you want to add, we're asking for a few very quite difficult things all at once, but then we can get this payoff. So it won't, the complexity, which essentially has to do with checking homotopy coherences, won't come up again in every step of every proof. That's sort of the big picture vision. So what have we done? So this project started in the fall, in September. Here's some background material. We had to contribute some background material and enrich category theory, and that allowed us to formalize the following definition. This is really more for the reference of those who want to take the slides home, but it's infinity cosmos is a category that's enriched in a particular way. And then there's a bunch of axioms about certain limits existing in a simplicially enriched sense, and then also some special morphisms called isofibrations being closed under various constructions. This is the Lean formalization of all of that. And, essentially the work that we had to do was explain to Lean what exactly these enriched limits are. This is sort of standard in enriched category theory, but was not yet in the Lean mathematics library. Okay. Keeping this high level, I'm going to go past the definition. One thing that our project has been doing, which I'm quite proud of, is rapidly sending things out to MathLib. So when we develop some background material that we think might be of more general interest, so we haven't attempted to PR the definition of infinity cosmos yet because it's not clear that anybody else besides us cares about that definition. But the sort of background things that are more general about this enriched category theory stuff, for a notion of co-discrete category, reflexive quivers, that sort of thing we have been sending out right away. You might know from experience that completing a PR can sometimes take quite a lot of time, and I think we were advised that we should be doing this early and often, and so that's what we've tried to do so far. Okay, so what I want to try and keep this talk understandable to a broad audience. So what I thought I would focus on is some of the challenges that have come up in the formalization. You'll note none of these really involve theorems about infinity categories. So the Infinity Cosmos project has not yet really proven any theorems about infinity categories. It's kind of a lot of background stuff that we've really been stuck on. And, anyway, that's one feature of this project, which is in contrast to the project that I'll describe in the third part of this talk. But anyway, that means these challenges, though, are a little bit more accessible. So one of the things that I mentioned that an infinity cosmos has a 2 categorical quotient. This is sort of the key ingredient to use formal category theory to prove theorems about infinity categories. We have not yet constructed that. One of the ingredients that went into this is a formalization that Mario Carneiro and I worked on over the summer of something called a reflexive quiver. So a quiver, remember, is a type together with Hom types. So it's a directed graph. It's type with sort of directed Hom types. Reflexive quiver just means you add the identities. So this is part of a category structure without composition or any axioms. And in fact, there's a free forgetful adjunction between categories and reflexive quivers. So if you have a category, you have sort of more structure than this. You can just forget to reflexive quiver. And then there's a way to freely generate a reflexive quiver on from a category. So this is something we needed. So we formalized it. This is in MATLAB, by the way. So this is past the PR process. So there's different strategies for proving that some functor is adjoint to some other functor. We used the triangle identities, and what this involves is a diagram chase. So here we are looking at a commutative diagram, or we're looking at a diagram of functors. So these are arrows inside the category of categories. And we needed to show that some composite of some functors was equal to some other composite of some other functors. That's what this proof is doing. What I've highlighted are the steps that I view as inessential. So when you do a diagram chase on paper, you have a whole bunch of arrows and you say, well, for some reason, these two can commute past these ones and you get something else. Those are sort of the essential steps in a diagram chase. But there's a whole bunch of unessential steps here that annoyed me and also meant that, this is not a proof I would have been able to formalize myself. Mario, as somebody who's a newer lean user, these sort of things are real impediments. I understand exactly how the proof should go on paper, and I absolutely would never have been able to formalize it in lean. What lean was confused about is, sort of what category we're working in when objects are type classes. So, lean, a category is sort of a type that has a instance of its category structure on it, and that's very convenient for a lot of purposes. I mean, when you want to refer to the category, you don't have to refer to all of the structure, but on the other hand, you're counting on the proof assistant for being able to elaborate all of that, and that was a complicated point of view. For most of MATLAB, a functor is thought of as a pretty big thing. You have some category, maybe you're working in the category of topological spaces, and you think about the fundamental group, which is a functor to the category of groups, and you're going to apply this functor to certain spaces, certain morphisms of spaces or whatever. You think of a functor as sort of a big thing, and there's sort of special notation for functors, which kind of looks like a sort of funny double arrow. But in this proof, a functor is just a morphism inside the category of categories. And so essentially, all the theorems about functors, the fact that composition is associative have been proven twice, once in one notation and once in the other notation. And a lot of this rewriting is saying that the identity as a morphism inside the category of categories is the same as the identity functor and so on. And all of this was extremely annoying. Getting those rewrites to be implemented was complicated and so on. So this is one sort of point of pain. And then another challenge arose in sort of formalizing some two-category theory. This is, not directly relevant to the Infinity Cosmos project, but this is something in MATLAB that I was involved in over the summer. And what I'm showing you is something called a pasting diagram inside a two-category. So you can think of the A, B, C, D as EF as objects in the two category. The arrows with sort of one leg on them are like the R1 and G1. Those are one-dimensional arrows. And then the arrows with a double arrow, those are the two-dimensional arrows, the two cells in the two category. And because all the one cells sort of point in the same direction and all the two cells point in the same direction, then this is composable. So there's a unique composite two cell that you get by sort of pasting all of this stuff together. Now, let's interpret this diagram in the two category of categories. So A, B, C, D, E, F are categories. All the single arrow things are functors, and all the double arrow things are natural transformations. And if the eta 2 and epsilon 2 are the unit and co-unit of an adjunction between the functors L2 and R2, then this middle part of the diagram, that little middle square, should cancel to the identity at L2. I mean, that's what one of the triangle identities of an adjunction says, is that pasted composite of natural transformations is the identity. And what this is essentially a formalization where that is the key step in the proof. So this has some implications for the theory of mates that I won't get into, but essentially it says that the pasted composite that I just displayed reduces, where I can just get rid of that middle square involving the eta 2 and the epsilon 2 because of left triangle components. So I've highlighted in green the sort of one step of this proof that is essential. The proof itself is considerably longer than this. And the reason is actually something that's kind of interesting about dependent type theory. So you saw in the definition of a one category that the arrows in a one category depend on it, they belong to a dependent type over the objects of the one category. And this makes it challenging to prove that one arrow is equal to some other arrow, because that proof might involve some heterogeneous equality, so might involve some sort of dependent equality. And this is even worse in two categories, because the two cells depend on both the boundary one cells as well as the boundary zero cells. So, you know, a difficulty in implementing the proof strategy that I just suggested, that we've got this eta 2 next to the epsilon 2 and they should just cancel, is that Riehl didn't even recognize that those whiskered natural transformations were composable, because you know, of some issues involving either dependent equalities or isomorphisms, depending on whether you're thinking sort of two categorically or bi-categorically. And in particular, so this is a proof that I formalized, and in my view, it's completely the wrong proof. I had to pass to the components of the natural transformation, which is not what I wanted to do. I mentioned this at a conference, Lean Together, sort of a week or two ago, and since then, Yuma Mizuno was able to give a better proof that generalizes. Yeah, so this is the sort of thing that I really think, you know, there should be some tactics that can help with. And he's developed a bi-category tactic that, you know, does allow him to give a better proof of that result and also a more general proof of that result. So because I passed the components, the proof that I formalized only holds in the two category of categories, where it should hold in a general bi-category, and the same argument should work in both cases. I would have liked to give this proof, but I wasn't able to do so, though he was. So here it is. It was I mean, this is a sort of expert level proof, however. So you can see that kind of the steps in it are some calculation involving this tactic bi-category, but you know, the user, so Yuma in this case, had to sort of write all this code in the purple boxes. So, you know, these are, you know, sort of, it's essentially putting parentheses in the pasting diagram that I explained before. You have to figure out exactly where to put the parentheses so that the bi-category tactic can apply. And I haven't tried to write a proof in this style, but I imagine that I would have a lot of difficulty with this. And again, I'm somebody who understands the sort of paper version of this theory quite well. So this is another case where I think there could be some automation to make this a bit easier for the user. And more to the point, this just illustrates the, you know, why, I mean, we've sort of made a lot of progress, and we also haven't made a lot of progress at the same time. So there's been a lot of formalization that I'm happy with. But, you know, if the point is to prove theorems about infinity categories, you know, that right adjoints preserve limits or something like that, we've kind of not made any progress towards that so far. But, you know, the project's only a few months old, and I'm sure we will get there at some point. Okay, so let me jump into the next project, and then I'll take some questions at the end if that's okay. Right, so the third idea to formalizing the theory of infinity categories is formalizing what I'll describe as synthetic infinity category theory in a particular, in a sort of domain-specific type theory. The one that this formalization proceeds in is something called simplicial homotopy type theory. It's in a special proof assistant called RZK. And let me try and explain sort of the idea of all of this. So let's go back to the original idea of an infinity category. It's supposed to be like a category, but you replace all the sets or types by infinity groupoids. You know, and this is just complicated to do in the traditional foundations of mathematics, because, you know, an infinity category just doesn't have a lot of sets involved, whereas in traditional foundations, sort of everything is a set or built out of sets. But there's another alternate foundation for mathematics called sort of homotopy type theory, where the primitive objects are these infinity groupoids, and that sort of brings the foundation a lot closer to the mathematical concept we're trying to reason about. So this is not a formalization in homotopy type theory, but in an extension of homotopy type theory called simplicial type theory. And let me explain just a little bit about how it works. So, so in ordinary sort of homotopy type theory, each type has a family of identity types whose terms we call paths. So really, this is sort of is maybe best thought about as like a different interpretation of the identity types then appears in, standard or Martin-Luft dependent type theory with extensional as opposed to intentional identity types. In particular, there's no rule that says that if P and Q are terms of the type X equals Y, then P and Q are equal. That rule is gone. And that is what makes these iterated identity types have equip A with some sort of infinity groupoid structure. So in the simplicial type theory, the simplicial extension of homotopy type theory, we also equip each type with a family of Hom types, whose terms we call arrows. So in addition to the paths, we have these arrows which are directed. So, paths are reversible. Arrows are not necessarily reversible. And in that background foundation, so explaining exactly what the foundation is a bit complicated. That's what's done in this paper. We can give a definition of an infinity category that's closer to the level that we like to think about it. So we say that a type in this system is an infinity category if. So the first thing I'll say is that any pair of arrows has a unique composite. So this is the kind of composition function that's a cornerstone of the ordinary definition of a one category. And then there's a second axiom that's maybe a little bit surprising, which is that connecting the paths to the isomorphisms in A. So using composition and then identities, which come for free, you can define isomorphisms in an infinity category. And if there's an equivalence between the paths and isomorphisms, or more precisely, if a specific map is an equivalence, then we say the type is an infinity category. And getting used to this formal system is, of course, difficult, though a proof assistant is a very useful way to learn how to write proofs in a new formal system because it helps you correct mistakes very quickly. But this definition is just a lot lower to the ground. In my experience, it sort of collapses the distance between infinity category theory and one category theory. And I want to try and give an illustration of that. So, okay, so firstly, the only way you could formalize anything in this system is if somebody wrote a proof assistant for it. This was done by Nikolai Kudasov, I think just kind of for fun. And it took us a while to discover that it existed. The proof assistant's called Rusk or RZK. And, so a main thing that it adds to ordinary dependent type theory is something called an extension type. And so types in this system are allowed to depend on things called shapes. I'm not going to really explain what the shapes are, but I'll point out the examples as we see them. And then one can form this new type, which is called an extension type. So given a shape inclusion, a type, and then a map from the smaller shape into the type, there's this type whose terms are maps from the larger shape into the type that restrict definitionally to the previous map on the smaller shape. So this is a very useful device. We don't have to assume a lot of axioms about these extension types. We can sort of prove various equivalences we want about, extensions on composites of shape inclusions and so on and so forth. So in particular, these extension types are how we define the Hom types that I mentioned before. So any type has a family of Hom types depending on two terms of type A, so a little x and a little y of type A. So here this involves a particular shape inclusion. Delta 1 is the one simplex, or the kind of free directed arrow. Its boundary is given by 2 points. And so if I map from the boundary into A, that's the same as just picking out two terms of type A. And if I extend to the directed arrow, then that's going to give me an arrow in A whose source is little x and whose target is little y. So this gives us direct access to this sort of Hom infinity groupoid in A from x to y, which is one of the sort of central data associated to an infinity category. And using extension types, I can also give a more precise statement of the composition axiom in an infinity category. So I'm going to call this a pre-infinity category because I'm leaving out this second axiom, which is connecting the paths with the isomorphisms. But a type is a pre-infinity category if every pair of arrows has a unique composite. What I actually meant by this is the following. So, so the data in sort of a simplicial model of infinity category theory, the data of a composition looks a little bit different than what you'd think. You can imagine having, a directed arrow from x to y, and then a directed arrow from y to z. So that's what this little f and little g give you. And together, you can think of that as some sort of horn shape where the two edges are directed arrows pointing in a compatible direction. And so having this F and G gives you that map into A. This horn can be filled into a triangle or a two simplex more precisely. The difference between a two simplex and the triangle is an orientation of the edges. The other edge is where the composite arrow lives, so that'll be an arrow from X to Z. But the two-dimensional data is some sort of homotopy witnessing the composition. And if you've sort of spent time thinking about the fundamental groupoid of topological space, for instance, this is sort of how composition works in there. The morphisms in the fundamental groupoid are somehow thought of as, based homotopy classes of paths. But if you represent those based homotopy classes of paths by actual paths, and then you ask sort of which paths could be the composite of two paths, you get this kind of triangle shape. And that's a way to think about all of that. So, what unique means in the language of homotopy type theory is that the type of all such is contractible, where contractible is sort of a standard definition in homotopy type theory. And what's wonderful is like, sort of semantically, this captures what's true for infinity categories, that composition is well defined up to a contractible moduli spaces of choices, but within the formal system, it behaves as if composition exists uniquely. So, really a term of this type that witnesses the composition is this entire two simplex mapping into A, whose boundary has a particular form, but you can sort of restrict to the bottom edge and then get a composite arrow from X to Z. And so you have a composition function that you have access to a composition function in this system like you do in one categories. And it just really makes your life a lot easier. And to illustrate that, I'm going to very, very briefly explain our formalization of, one other thing. So a pre-infinity category has identity arrows for free. You can just, essentially, you can always, if you're trying to come up with an arrow from X to X, you can use the constant function, and that defines the identity arrow. And similarly, in a pre-infinity category, you can prove that any arrow F is equal to F composed with an appropriate identity on either side by just inhabiting these types that are contractible. So we get, so the reason that the definition of a pre-infinity category didn't refer to identities or associativity is actually all of those are theorems. I'm not going to discuss associativity now for time reasons, but okay. So what I do want to do is tell you briefly about the innate lemma. So in contrast to, the disadvantage of this system is that, it's sort of specialized. So it's harder to become used to. We're using a sort of tiny proof assistant where we had to formalize absolutely everything from scratch. We can't sort of automatically extract the formalizations in RZK to get formalizations in some other proof assistant. So it's sort of its own isolated world. But the advantage is we can prove serious theorems about infinity categories, and they're not too painful. So an example of that is the innate lemma. And what it says is that evaluation at the identity defines an equivalence between the type in brackets should be thought about as the type of natural transformations between the representable functors at a little a and a little b, and then just the Hom type. And there's something that's interesting that goes into the statement here. So, if I were teaching a one category theory class and I explained what a natural transformation is, a natural transformation, that definition has sort of two pieces. One are something that you might call the components of a natural transformation, and that's just the family of maps phi that we have on display here. So for every term Z, I have an arrow phi Z from the Hom from Z to A to the Hom from Z to B. But then there's usually a naturality condition. And actually that comes for free in this system as well. So, the reason that we're not, really tearing our hair out to prove that some construction extends to a homotopy coherent infinity functor, that some family of maps extends to an infinity natural transformation is all of this is sort of formal in the formal system. This is kind of like when you're doing constructive mathematics, it's very difficult to write a discontinuous function for sort of similar reasons. Any family of maps is automatically a natural transformation. So that's pretty cool. So, right. And so so the statement of an infinity categorical unit lemma is somehow simpler than the statement of the one categorical unit lemma because it refers to this concept of a natural transformation, which is much simpler somehow in this system than it is in one category theory. And then the proof is simpler as well, because usually in the proof you have to prove something or other is natural, and that just comes along for free. So what the unit lemma says is that a particular map defined by evaluating at the identity defines an equivalence. And there's a standard way to construct the inverse. If you give yourself an arrow V from little a to little b, and then you give yourself an arrow F from little x to little a, you can just compose those and get an arrow from little x to little b, and that's the definition of this natural transformation that comes from an arrow, and then you have to check that the composites each way around are pointwise equal to the identity, and this follows from the identity laws, and from the identity laws plus naturality. So it's a pretty simple check, both when we're writing in the a proof in the simplicial type theory on paper and also in the formalization. So there's a website that Nikolai's done this sort of clever setup. So when we write formalizations in RZK, we put them in sort of code blocks inside markdown files so that the sort of expository text displays nicely. Here's the definition of the evaluation and identity functors and the unita functor, which is the inverse functor. This slash here is a shorthand for lambda. So it just says, given your V and your Z and your F, then you define something or other to be the composite. One thing to maybe point out is, RZK is a experimental proof assistant, and one thing that has not been implemented yet is implicit arguments. So the composite of F with V, that's this thing that appears at the very bottom of the page, is we can't introduce some shorthand notation like F composed V for that. We have to sort of write out all of the arguments, unfortunately, but in the future, hopefully that'll be different. And then, this is essentially the formalization of the proof. So we need to check that some composite is the identity and the other composite is the identity. I have to use function extensionality twice to kind of connect it back around. So similarly, we have a whole bunch of contributors, and we'd love to have people contribute there. And I'll stop here and take some questions.
Thank you. Are there any questions in the room? There's one question.
Sure.
Yeah, so in the third formalization you mentioned, I noticed that there's you didn't mention any hierarchy on the level of morphisms in this model, and I'm wondering if that is the case, we don't have the definition of some one morphisms, two morphisms, and we're just dealing with the syntactic definitions here.
Yeah, sure. So right. Okay. Yeah, so somehow, right. So what we have directly in the simplicial type theory are these Hom types. And Hom types are essentially, they're like types of maps from a delta 1 into A. Delta 1 is like the free living one morphism, where I've specified I want the source to be exactly this and the target to be exactly this. So using judgmental equality as opposed to, the equality that you have to prove. So there's a few different ways I could access the higher morphisms in an infinity category. So what you remembered is that an infinity category should have not just one-dimensional morphisms, but two-dimensional morphisms and three-dimensional morphisms. So a way to access a higher morphism would be, on the one hand, to map from the 2 simplex into A. That will pick out a higher morphism. Or essentially by currying, I could map from a 1 simplex into this Hom type from X to Y, and then I would get a 2-dimensional morphism between 1-dimensional morphisms from X to Y. So that's sort of maybe a more direct way to access a 2-cell. And there's a relationship between those two perspectives. And I had mentioned here that you're able to, oh, look, I can't highlight. great. So I'm able to prove equivalences between extension types, and that makes those sort of relationships into theorems. So, somehow, the high level summary is somehow these Hom types, even though the points are just one-dimensional morphisms, they have some sort of higher structure, which contains the two morphisms and the three morphisms and all the way along. And sort of the magic of type theory is when I mentioned in this discussion of naturality for free, if I'm trying to define a map from here to here, this is just a function in type theory. And so I say, well, for all f in the domain, do some manipulation, and now I get an arrow in the codomain. It feels like I'm just defining this as a function on the one-dimensional arrows. But because, sort of definitions in type theory must hold in an arbitrary context, really by doing it at the level of the arrows, I'm also automatically doing it at the level of the higher arrows. And that idea is what goes into the proof of this, naturality for free statement. What you see is that this function phi of z is actually a map not just on the one-dimensional stuff, but also on the two-dimensional stuff. And that goes into the proof of naturality. So it's sort of an interesting setup where the higher thing is there and you can access it when you need it. Proving associativity, similarly, you're accessing the higher structure that's in these Homs, but you can also sort of forget about it and pretend you're working with a one category, and that's mostly a correct experience. So.
See, thank you.
Sure.
Thank you. Are there any other questions? Doesn't seem like it, and I don't think there are any questions online either.
Okay.
Yeah, in that case, let's thank the speaker again. Any questions?
So I mean, I guess I'm curious about like how many of Riehl's axioms you need to remove and how many axioms you need to add to get to the RZK type theory. Like
yeah, I think it should. So I'm not really an expert in type theory, to be honest, but I think this should be understood as more complicated than that. So I mean, the first thing to say is that the treatment of equality in lean and the treatment of equality in homotopy type theory are totally different. And it's not. You can't just sort of, in AGDA, you can flag without K or whatever, and now you lose the rule that says if P and Q are terms of type X equals Y, then P equals Q, and then you're doing homotopy type theory, basically. So that's not possible in lean because of something or other about something that's in the kernel. That's way above my pay grade. So that's one issue is sort of the gap between the dependent type theory in lean and the dependent type theory in homotopy type theory. But really what RZK is doing as well is the contexts are more complicated. So usually you think of a context as just given by some other types and maybe some dependent types. But here our contexts actually have three different layers. The bottom two layers give us these simplicial shapes, which I didn't explain at all how that setup works up type theoretically, but essentially sort of before we even introduce types at all, we have these syntactically defined simplicial shapes and maps between simplicial shapes, and everything's allowed to depend on that. So so context could potentially involve shapes. Maybe there's no shape, and then it's just sort of an ordinary context in homotopy type theory. But potentially we have these shapes, and then we have a homotopy type theory or a dependent type theory layer, and all of that. And anyway, so that's the difference between the systems. How that goes into implementation, that's a much better question for Nikolai than for me. So I know he did this in Haskell, the slide with RZK. He's written a paper about it and given some talks about it. He had to do a lot of geometry to sort of set this up correctly. So and a lot of the sort of things that RZK is, he's implemented something called a tope solver, which will help RZK sort of check that, you can think about a commutative square as being two triangles glued together and something like that. And it really makes it pretty usable. So he's done a lot of I think there are a lot of interesting ideas that went into the development of this proof assistant. So.
Well, yeah.
I had a quick question about what you just mentioned.
Sure.
So are all these shapes, like the various horns and the triangles and simplices and so on, are they considered as types themselves, like in the foundations of this proof assistant, or are they like a separate entity?
Yeah, we do not consider them as types. So there are lots of variants in directed type theory and also in simplicial type theory. And sometimes they are thought of as types, but not here.
Okay.
So yeah. So yeah, in particular, you don't map into them. They don't have identity types. The idea is the shapes are some sort of like, they're just used for mapping out. And so there's sort of something that you can work with a bit more strictly, which is something I could give some intuition for in the language of Quillen model categories, if that would be helpful. But they're like cofibrant or something like that. These are the cofibrations, if that's a term you've heard. So, or the shape inclusions really are the cofibrations. So.
Okay.
But it's sort of, yeah. There are other approaches to this. It's not clear that any of this is, that it's essential to introduce the shapes. Alternatively, you could have some kind of directed higher inductive type that you could use to define the sort of shapes that you want. And what you would lose is some judgmental equality. And then replace the extension types by sort of ordinary function types or dependent function types. And what you would lose is some sort of judgmental equality. You would have to prove that the source of an arrow is equal to little x and the target is equal to little y. And Mike Schulman and I had the instinct that that would be a real pain, but maybe it's not so bad. We don't actually know.